This episode explores the paper titled Galactic Gravitational Field Measurements, Part 3, Galaxy Clusters, authored by Christopher Young, which extends the galactic energy flow framework to the scale of galaxy clusters. The purpose is to demonstrate how energy dynamics within the auxiliary modulation coordinate can explain cluster-scale gravitational phenomena without invoking dark matter. The paper begins by situating itself within ongoing astrophysical challenges, notably the persistent puzzle of galactic rotation curves. Since Vera Rubin's seminal work in the 1970s, observations have shown stars and gas in the outer regions of galaxies orbit at nearly constant velocities, contradicting classical Newtonian predictions that orbital velocity should decrease with distance from the galactic center. This discrepancy has traditionally been addressed by hypothesizing dark matter halos enveloping galaxies. However, despite decades of effort, direct detection of dark matter remains elusive, raising questions about whether alternative explanations might better account for the observed phenomena. Dark matter models, while successful in many respects, face several limitations. First, the absence of direct detection challenges their physical reality. Second, the required dark matter distributions often involve fine-tuning without clear physical principles, leading to ad hoc models. Third, small-scale discrepancies, such as the missing satellites and Corcus problems, highlight conflicts between predictions and observations. Finally, the philosophical concern arises about positing a dominant yet undetectable form of matter. These limitations have motivated alternative theories, including emergent gravity and modified dynamics. Building upon Verlinde's emergent gravity theory, which reconceptualizes gravity as an entropic force arising from microscopic degrees of freedom, this paper proposes a specific mechanism, energy flow through the auxiliary modulation coordinate. This coordinate is a structured modulating energy field existing parallel to spacetime, encoding energy dynamics, quantum behavior, and field interactions as wave-based resonance patterns. The framework shifts from a mass-centric view to an energy flow perspective. Galaxies are modeled not as passive mass aggregates, but as dynamic energy flow systems, sustained by continuous energy injection from central supermassive black holes. These black holes convert accreted matter into energy that propagates through the auxiliary modulation coordinate, modulating spacetime elasticity gradients and maintaining galactic structure. Mathematically, the energy flow is governed by a generalized modulation-based field equation that unifies space, time, and modulation dimensions. The framework introduces four fundamental dynamic processes within the auxiliary modulation coordinate: information flow, baseline resonance, rotational coherence, and localized stable structures. Together, these processes produce energy flow patterns that sustain spacetime curvature and explain galactic rotation curves as boundary phenomena emerging from curvature resonances within the modulation lattice. A key concept introduced is spacetime elasticity, the ability of spacetime to respond differentially to energy flow based on local conditions. This elasticity peaks at galactic boundaries, creating low-resistance zones that enable sustained orbital motion without requiring dark matter's gravitational influence. The elasticity is modeled with an exponential decay function, providing a physical mechanism for the modified gravitational behavior observed at galaxy edges. At the core of energy injection are supermassive black holes, such as Sagittarius A Sti in the Milky Way. The paper quantifies the energy output from Sagittarius A using observed mass and accretion rates, calculating an energy output on the order of 10^42 joules per year. This energy drives the modulation field, initiating structured energy flow throughout the galaxy. The paper extends this framework to galaxy clusters, which exhibit a hierarchical, bubble-within-bubble energy architecture. The intracluster medium, ICM, is identified as the primary carrier of energy flow, accounting for 80 to 90% of the baryonic energy contribution to spacetime curvature in clusters. Individual galaxies and galaxy groups contribute nested energy fields within the larger ICM energy field. Energy exchange between galaxies and the ICM is modeled via inflow and outflow coupling coefficients, with active galactic nuclei injecting significant energy into the ICM through jets and outflows. This nested energy structure produces composite spacetime curvature profiles with attenuation functions describing the decay of individual galaxy contributions with distance. The emergent gravitational behavior from these nested structures explains enhanced gravitational lensing, velocity dispersion profiles of member galaxies, and the stability of substructures within clusters, all without invoking dark matter halos. Quantitative analysis of representative galaxy clusters uses observed parameters such as total baryonic mass, ICM mass fraction, number of member galaxies, cluster radius, central ICM density, and temperature. Calculations of energy density, spacetime curvature, velocity dispersion, and gravitational lensing angles align closely with observational data across poor, rich, and massive clusters. For example, predicted velocity dispersions range from 400 to 1500 kilometers per second, matching observed values, and lensing deflection angles correspond well with measured strong lensing arcs. A detailed case study focuses on the bullet cluster, long cited as direct evidence for dark matter due to the observed separation between X-ray emitting gas and gravitational lensing centers. The conventional interpretation attributes this to dark matter halos passing through each other during the collision, while the ICM is slowed by ram pressure. However, this explanation faces challenges, including the nature of dark matter particle interactions and the spatial correlation of galaxies with lensing mass. The presented framework offers an alternative interpretation. Energy flows in the auxiliary modulation coordinate dimension propagate differently than baryonic matter. During the collision, the ICM energy fields interact and are disrupted, but the galactic energy fields, supported by active nuclei, maintain coherence and pass through with minimal interaction. This differential behavior naturally produces the observed separation between X-ray and lensing maps. Quantitative calculations for the bullet cluster incorporate observational data on baryonic mass, ICM temperature and density, velocity dispersions, and relative collision velocity. Energy densities are computed using rest mass energy equivalents modulated by auxiliary modulation coordinate coupling functions, which differ for the ICM and galactic components. The ram pressure experienced by the ICM during collision is calculated, confirming significant disruption, while the transmission coefficient for auxiliary modulation coordinate energy fields is near unity, indicating almost unimpeded passage. Post-collision energy distributions combine displaced ICM components and galactic energy fields. Spacetime curvature and gravitational lensing deflection angles are derived from these energy densities, yielding values consistent with observed strong lensing features. The framework reproduces the effective mass-to-light ratio traditionally attributed to dark matter without invoking unseen mass, demonstrating quantitative agreement. Furthermore, the paper models the X-ray emission resulting from shock heating in the ICM during collision, predicting post-shock temperatures consistent with observations. Entropy-resolved resonance profile analysis characterizes the bullet cluster as a double bubble energy structure, with distinct ICM and galactic energy fields propagating through each other. The implications of this analysis are significant. The bullet cluster does not necessitate dark matter to explain its gravitational lensing and X-ray observations. Instead, energy flow dynamics within the auxiliary modulation coordinate provide a comprehensive explanation. The framework also makes several distinctive, testable predictions. It anticipates characteristic turbulence patterns in the ICM with modulated power spectra detectable via high-resolution X-ray spectroscopy from missions like XRESM and Athena. It predicts systematic misalignments between X-ray temperature peaks and gravitational lensing centers in non-merging clusters, scaling with cluster mass. Active galactic nuclei are expected to enhance local gravitational lensing strength, producing detectable hotspots in lensing maps. Additionally, enhanced spacetime elasticity at cluster edges should manifest as modified galaxy velocity distributions, enhanced tangential alignment of weakly lensed background galaxies, and characteristic velocity dispersion profiles near cluster boundaries. To validate these predictions, the paper proposes observational strategies including multi-wavelength surveys combining X-ray, optical, and lensing data across large cluster samples, high-resolution ICM dynamics measurements, detailed strong lensing network analyses, and radio observations of cluster magnetic fields. Statistical methods such as Bayesian model comparison, parameter estimation consistency tests, and blind analysis challenges are suggested to rigorously evaluate the framework against conventional dark matter models. In conclusion, this work extends the galactic energy flow framework to galaxy cluster scales, explaining gravitational phenomena without dark matter by modeling clusters as cosmic-scale energy processing networks. The intracluster medium serves as a key energy carrier within the auxiliary modulation coordinate, and supermassive black holes act as localized energy injectors, sustaining cluster dynamics. The framework reproduces observed cluster properties including velocity dispersions, gravitational lensing, and X-ray emissions across cluster masses. The bullet cluster's observed features are naturally explained through differential energy flow dynamics, challenging the necessity of dark matter. The framework offers specific predictions that can be empirically tested, potentially reshaping our understanding of cosmic structure formation and gravitation. This comprehensive analysis suggests a paradigm shift from mass-based gravitational models to energy flow-based interpretations, integrating quantum field theory, thermodynamics, and space-time elasticity into a unified description of galaxy cluster dynamics. Further observational validation will determine the framework's role in future cosmological theories.